Okay, great. So we're moving on now from the topic of deep learning to talk a little bit about contours and how we can track objects in images and detect objects in images based on the shape of their contour. So we're going to cover next week some techniques around active contours, sometimes called snakes, which are a little bit like, you can think of it like an elastic band that kind of moves around an image and snaps onto the object that you're looking for. And we'll talk about other kinds of contour model as well, like PDMs, which are statistical models of shape that help us track objects more robustly. We saw one example of those actually in that leaf tracking example I showed you of the particle filter last time. But before we can talk about any of those applications of contours to computer vision, we first have to look at the basic mathematics of curves and contours so that we can think about how we can model those curves. So that's the topic of the lecture today. We're going to start by talking about different ways that we can represent a line, specifically the explicit, implicit, and parametric forms of a line. And then we're going to look at the parametric form of a line, generalize it to a cubic curve, and then look at ways that we can manipulate cubic curves in order to represent shape in computer vision, and in graphics actually as well. So then we're going to look at a couple of curve families, specifically the Hermite-Bezier curves, and then look at a couple of spline families as well, kappa and beta splines. And finally, assuming there's time, there may not quite be enough time today, we'll see, we'll talk about the Frenet frame. Okay, so as I say, yeah, the motivation really is to introduce some basic mathematics so that we can start fitting curves to objects that we see in images. So, for example, these two screenshots are taken from a tracker that's running as particle filter, and instead of tracking the object in a two-dimensional space, actually we're modeling a high-dimensional space that can represent curves and modeling the object by tracking through trajectories in that higher dimensional space. So really this is an intro to this whole topic today. Okay, so if I were to ask you to give me the equation for a line, I reckon 95% of you will immediately say, oh, y equals mx plus c. That's an equation for a line. It's the one we all learn first in school, and it's a convenient form for representing a line because it allows us to represent the gradient of the line here by this constant m, and also the intercept that the line makes with the y-axis by this constant c. And it's convenient in that respect, but it's actually inconvenient in others because it limits the range of possible representations of a line we can make. Specifically, we can't represent one type of line with this. What is it? A vertical line, that's right. Because with a vertical line, you've got multiple values of y for a given x. So it's not just y equals mx plus c that's the issue here, it's the fact that we're just generally representing a line in the form y equals some f of x that causes us that problem. So the explicit form of a line is really useful if we've got, say, one coordinate and we want to get the other coordinates in terms of the first, so y equals mx plus c, and we'll see that later in the course we'll talk about explicit forms of equations for things like circles, where there are more variables on the right-hand side than the left. But in general, this form of line is not something we're going to be talking about today because we have this limitation on the range of possible lines it can represent. So for the purposes of today and the rest of this topic, the more convenient form to represent a line in is what we call the parametric form of a line. Okay, so in the parametric form of a line, we have an equation such as this one here, where we have a point on the line being parameterized by this dummy parameter s, which lets us walk along the line. So in this equation, and actually for the rest of this lecture, I'm underlining the vector quantities here. So every underlined quantity here is a vector. In this example, it's a two-dimensional vector, but this idea generalizes to lines through any dimensional space. So 3 would be fine, for example. But in this parametric form of a line, we start at a particular position that we call x0, and then we move along the line in units of this quantity x1, which is a vector that points along the line. So in this diagram here on the side, we've got a starting point here, this is our x0, and then we're moving along one lot of x1, two lots of x1, three lots of x1, all the way up to infinity. And in fact, that value s doesn't have to be integer, it can be any real value. So it could even let us walk fractional amounts of x1 or even negative amounts of x1. And that traces out then an infinitely long line. Is everyone happy with that there? So s is not something that defines the shape of a line, it's a parameter that lets us iterate along the line. Okay, so the parametric form of a line is convenient because it lets us represent lines in any direction, including vertical lines. And it also has this useful property that we can iterate along the line very easily. Okay. The third form of a line that we sometimes use in computer graphics and vision is what we call the implicit form of a line. And in the implicit form of a line, we have a function that takes in all of the parameters of the variables of the space. So we're working in 2D here. So in this case, it's f of x and y, those being our two dimensions of the space. And we say that that function is defined such that any point on the line will return us 0 if that point is on the line. Okay, so this is called the implicit form of a line. And you can see that we can get very easily from the parametric form to the implicit form of a line by just rearranging it. If I were to take this equation for the parametric form of a line here, which we just talked about on the previous slide, P of s is x0 plus sx1, and I were to just write it out, each of its components, so let's say this is two-dimensional, let's say the x component is just the starting position x plus some s times u, where u is the x component of the x1 vector. Okay, and similarly, I've got y equals the y component of this starting position plus s lots of v, which is the y component of the x1 vector. If I just write that equation out then in these two component forms and then rearrange these for s, so I'm going to put s on the left-hand side, then what I'm doing here then is just subtracting subtracting x0, dividing by u, and that gives me an expression for s, which is this expression here. So x minus x0 over u is equal to s. And if I do the same for this equation here, then I can define an equivalence between this, x minus x0 over u equals y minus y0 over v. And remember, our mission here is to come up with a function that takes as input x and y and returns us a 0. So let's rearrange that equation so that all of the unknowns are on one side, and so all the variables on one side, and we have a 0 on the other. So we're going to multiply this by u and by v, which gives us this expression here, and then subtract one side for the other gives us this expression down here. Yeah. So you can see in this equation here we have the implicit form of a line because, as I discussed, x0 and u and y0 and v, these are just constants. These are defining the shape of the line. If we model a line, this is how we define where it is and where it goes. Yeah. So the only variables on this side are x and y. So can you see that this is then an implicit form for the line? Yeah. Anyone got any questions on that at all? Okay. So what's the use of the implicit form of a line? Well, the implicit form of a line lets us determine very quickly whether we are not only on the line, if some point x, y equals 0, but also whether we're on one side of the line or the other side, because this equation will evaluate positive if we're on one side of the line and negative if we're on the other, okay, depending on which way around the format the function is defined. So this is really useful in something like a computer game, for example. So there's an operation in computer games called clipping, where you try and figure out if you've walked through a wall or not in the game. Okay, some cheats turn clipping off, so you can do that. So you know, the clipping operation is something that's frequently done using an implicit form well, actually in 3D of a patch, but anyway. So these three representations of a line all have different properties. The first, the explicit form, lets us very easily get one coordinate in terms of another, but it doesn't model all possible lines. The parametric and the implicit forms, the second and third types that we've looked at today, you can model lines that go in all directions, but they have very different properties. The parametric equation lets us iterate along the line easily. That's very hard to do in the implicit form. And the implicit form lets us detect whether we're on or to one side or the other side of a line. That's very hard to do with the parametric form, yeah? Okay, so is everyone happy with the sort of advantages and disadvantages of these three forms of line? So we're going to look at the parametric form today, and we're going to look at the parametric form not just of a line, but actually of a curve. So we just talked about how the parametric form of a line is represented as some x0 plus s lots of x1. Yeah, that gives us our position at a particular location s on the line. By the way, the convention in this equation is to have s iterate between 0 and 1. Okay, so we try and define our equation so that happens. So if we go from p of 0 all the way to p of 1, we'll go from the start of our line to the end of our line. Okay. Now, what would happen if I add an additional term to this equation? What if I add, for example, this term s squared lots of x2? So I've got a new vector in my equation now, x2, and I'm pre-multiplying that by s squared. Okay, so this equation has now turned from a linear equation with respect to s to a quadratic equation with respect to s. Okay, so we can expect that as we increase our value of s from 0 to 1, we're going to trace out in general a parabola in our space. Okay, so we have a curve that can turn at most once. Yeah. And if we have an additional term, maybe we keep adding terms. Maybe we add a cubic term. Now we have a cubic equation in terms of s, which traces out a cubic curve, a curve of order 3, which therefore can turn at most 2 times. So in principle, we could model any curved shape of increasing complexity by just adding on increasing powers of s to this equation in order to get curves that could turn maybe, I don't know, 20 times if I had an equation of polynomial order 21, for example. Yeah? Everyone happy for this so far? And also, can you see how these terms, if we were to think about this P of s as modelling a particle moving along this line, you can see that x1 is equivalent to what? If you consider s to be time, what would x1 be equivalent to for that particle? It's velocity, yeah? Yeah, the vector in which it's moving. What about s2? Okay, it's going to be the change in velocity, isn't it? Yeah, so that'll be the acceleration. What about s3? The rate of change of acceleration, sometimes called the jerk. So that is, yeah, as we increasingly add these polynomial terms, we can get curves that are able to represent more complex shapes. But in practical terms, if I were to take a shape, like this shape here, which you have to take my word for it, it's going to be the shape of a teapot, okay? And I wanted to model the shape of this teapot using one of those curves, P of s, then that's going to be a really tricky thing to do, because I've got to come up with not only the velocity, the acceleration, the rate of change of acceleration, the rate of change of acceleration, the rate of change of acceleration, and so on, in order to get my curve to exactly pass along this path. That's going to be a really difficult thing to figure out how to do, right? So if we do even approximate it well, what we'll find is the curve often overfits the shape that we want to make and undulates or wobbles around the trajectory we want it to take. So it's very hard to control complex polynomials like that to trace out a shape like a teapot, which might conceivably be something we're interested in detecting in an image, for example, bringing it back to computer vision. So what we do instead is, in computer vision and in graphics actually, we model the shape of a teapot or more complex shapes generally, using piecewise cubic curves. That means we basically approximate the shape of an object using a collection of cubic curves that join together. Okay, we call that piecewise modeling, right? So, for example, this green curve would be one piece, this blue would be another, this magenta would be another, and so on. So each time we're modeling a piece of curve here, we're using a cubic curve. And generally speaking, as a rule of thumb, just convention in vision and graphics, we won't really go beyond a cubic curve in terms of the complexity for modeling each of those pieces of curve. Okay? So each one of those bits of curve then is modeled by its own equation, P of s equals x0, x1. So basically its own set of vectors x0 through x3 for each piece of curve there. Yeah? Everyone got that? Okay, so we've just got to... Oh, yeah. No. Yeah, well, okay, that's a good question. Yeah, I mean, obviously a cubic curve can represent a straight line as well. So usually we just use cubic curves. Yeah, you'll see in a moment it's quite useful to be able to have just a general repeatable equation for this rather than specific equations for each piece. Okay, so our job then is if we're doing piecewise modeling, is to figure out a way of joining up these curves to make our full shape. And in order to do that, we have to start talking about what it means for curves to be joined up, what we say to be continuous in graphical modeling. So it turns out that there are actually different ways that we can define continuity. So the most, I guess, naive, simplistic form of continuity is when we have one curve that ends and then the second curve begins at the end point of the first curve. So the join joins the two curves together, so they're contiguous. This kind of continuity is what we call C0 continuity. We have this notation that we introduce, C, capital C with a superscript, to describe the different orders of continuity of a curve. And this one is continuous C0 because although the start and end points meet at the same point, actually higher order derivatives of that equation, of that cubic curve equation, are not continuous, okay? So you can kind of see that here. If I were moving along this blue curve here as a particle, and I'm moving along at a particular velocity, and my velocity vector is pointing in this direction here at this point, then suddenly I'm on curve 2, my velocity vector is pointing in this direction, yeah? So although the curves are continuous up to their 0th derivative, their position, they're not continuous in their first derivative. So that's why this is a C0 continuous curve. But an example of a C1 continuous curve, which is not only C0 continuous, but is also C1 continuous, that's part of the definition of it being a C1 curve, so it has that property, we see that the curves start and end points and their start and end tangents, i.e. velocities to those curves, match up. Yeah? So they're continuous in their 0th and first derivative. Everyone happy with that definition? So in general, we can have curves that are continuous up to Cn continuity, but in practice we tend to only work with C1, occasionally C2, but usually just up to C1 continuous curves. So these piecewise curves are a really useful modelling technique in graphics and computer vision, but we still have to manipulate the position, velocity, acceleration, rate of change of acceleration of each of those curve pieces in order to make sure they join up with, say, for example, C1 continuity. And that's quite hard to do. Imagine you were throwing a ball, and you had you've got a start position and a velocity, and your acceleration is gravity, so you've got that too, and we don't have a really rate of change of acceleration. That maybe we've got a little rocket booster on the ball or something, and we're trying to throw it and calibrate our rocket booster and calibrate our velocity and change our value of gravity to make sure our curve ends up in exactly the right place. So that and such that it starts with exactly the right velocity and position for the second curve. Coming up just with those numbers is not at first glance a straightforward thing to do. So that's why we start thinking about how we can work with families of curve, and we're going to start talking about those in a moment. So just before we do that, let's just introduce a notational convenience here. We've talked several times now about this equation here, which is the cubic equation for a curve, a parametric curve. What we're going to do is rewrite this equation now in a matrix form, okay? So here we've got two matrices, actually. We've got a matrix here that contains these x's, which remember is the start point, the velocity, the acceleration, the rate of change of acceleration, yeah? And we have here a vector which contains all the parameters, the s's of their different order, okay? So actually, so these are both, matrices. You can see that this is a matrix because each one of these vectors, in actual fact, is going to be a column in here, right? If it's two-dimensional, then this is going to be 2 by 4. If it's three-dimensional, because we're working in three-dimensional space, it's going to be 3 by 4, and so on. And then this is just a vector, but I mean, in general, that's a matrix. So we could introduce this notation, and hopefully everyone can see that multiplying this with this matrix recovers us this equation. Yeah? Everyone happy with that? We take this equation, remember, matrix multiplication, we take the row, lay it on top of the column, place for place multiply, sum it up, that gives us our output. Yeah? Okay? So let's call this matrix C, and let's call this matrix Q, but more precisely we'll call it Q of S, because it's parameterized by S. These are just constants, yeah? So I'm going to double underline matrices from now on. Single underline means vector, double underline means matrix. So our vector is a result of this matrix multiplication. Everyone happy with that? Okay, so C is controlling the shape of the curve, the position, the velocity, acceleration, rate of change of acceleration, and so on. And the Q is controlling where we are. It's parameterizing our curve. It's letting us iterate along the path of the curve. And as I say, by convention, we try and have this curve iterate from P of 0 to P of 1. Okay, I think I already gave the game away to that question. It's position, velocity, acceleration, rate of change of acceleration. Okay, so as I say, it's quite hard to manipulate a curve by controlling its position, velocity, acceleration, rate of change of acceleration. It's easier to control the curve in spatial terms by saying, I'd like to define a curve that passes through these bunch of points, or maybe passes through a couple of points with particular velocities. That's a more controllable way to define a curve. So in order to control the curve this way, what we're going to do is introduce into this equation P equals CQ we're going to introduce a new matrix here, which is a 4 by 4 matrix slotted in the middle here. And this matrix we're going to call M, and it is the blending matrix, okay? And this allows us to change the meaning of the vectors that exist here in this left-hand matrix, which no longer, your left-hand matrix, which we're no longer going to call C, we're going to call it G now, okay? G for geometry matrix, okay? Just to underline the fact that this matrix here defines the geometry or shape of the curve, this G here. M is the blending matrix, which defines the meaning of these vectors in G, and Q is, as before, just the parameter matrix that takes us iterating along the curve. Everyone happy with that? Right, any questions on any of this so far? So the takeaway message from this slide, it's super important, okay, P of S is equal to GMQ of S. That is our general framework now for a parametric cubic curve. G defines the shape, M defines the family of curve we're dealing with, we'll see what that means in a moment, and Q defines where we are on the curve, and it goes from 0 to 1. Okay? Okay, so let's look at the first family of curves we're going to deal with today. These are called the Hermite curves, and the Hermite curve makes it very easy to define a curve that has a particular start and end position and velocity. So with a Hermite curve, by introducing this matrix here of these 16 numbers, we'll talk about why these numbers are these numbers later on in about 2 slides' time, but let's just believe me, these are the numbers for now. Okay? By introducing this matrix of numbers, we change the meaning of G such that the first vector in it defines the start point of the curve. We use the notation P of 0 as shorthand for that because we know that curves start at S equals 0. The second vector defines the end point of the curve. So imagine this is the blue curve here. That's the start point, that's the end point. P dash of 0, the little dash here is indicating first derivative, okay? So that means the first derivative of the curve at the start. So in other words, it's velocity at the beginning of the curve. That corresponds to this green, that's actually an arrow, this green vector pointing upwards, okay? And then similarly, P dash of 1 is this vector pointing downwards, okay? So that's the end tangent to this blue curve. So hopefully it's easy to see how we would come up with 2 curves then, this blue and this red curve that are joined with C1 continuity. It's as straightforward as what? If I've defined my blue curve using one of these matrices, one of these equations, how would I define my red curve? Yeah. 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 Absolutely, perfect, thank you. Yes, so for the second curve, the red curve here, I just use the end position and tangent as the start position and tangent of the second curve, and then I make that curve end wherever I want with whatever velocity I want. Okay, thank you. Okay, maybe we'll do a quick demo of that. Again, this won't come out on the video due to limitations in Panopto, so all the more reason to come to lectures. So let's define an S that goes from 0 in small increments all the way up to 1. Okay? And let's define a G, that geometry matrix G, to define where our curve is going to be. So let's start our curve at the origin, 0, 0. Okay? And then we're going to end our curve at some point, let's say 9, 0. Okay, so 9 along x, 0 along y. And let's start the curve with a vector, a velocity vector that's pointing directly up. So that would be 0, 1. And we'll end the curve with a vector that's pointing directly down. So that'll be 0, minus 1. So that's our geometry matrix right there. Okay. Now let's just define our M as that constant matrix that is that bunch of 16 numbers. So 2 minus 3, 0, 1, minus 2, 3, 0, 0. 1 minus 2, 1, 0, 1 minus 1, 0, 0. What on earth does that mean? Well, we'll find out soon enough. There it is. Okay, and now we're going to define our Q, and I'm going to take a shortcut here with my Q. Instead of just putting a single value of S as one column of Q, okay, I'm going to put all the values of S. So I'm going to define a Q that has a column in it for every value of S. So it's going to start with S being 0, so the first column will be 0, 0, 0, 1, and the last column is going to be S cubed, S squared, S1, so it's going to be 1, 1, 1, 1, but all the values will be in between. So let me show you that. So we've got S cubed, S squared, S, and we're going to have ones that are the size of S. So there's my Q. So my Q in this example, worked example in MATLAB, is not just one column, it's multiple columns. Okay, you can see this is the end column here where S is 1. Right at the beginning, there was a column where S is 0, somewhere up there. Okay, so let's multiply that together then. P equals G times M times Q. That gives me a whole bunch of points now. Normally P equals GMQ would give me just 1 point because I'd have just one column in X. But because I put multiple columns in X, sorry, so let me say that again. Normally P equals GMQ would give me 1 P because I'd have one column in Q. Because I've got multiple columns in Q, I'm going to get multiple P's out, yeah? So these are the P's that I've got out. Let's plot them. In blue. Where did my plot go? Nowhere. Oh no, there we go. Right. And there we have it. So we have a curve, a single curve that starts at 0, 0, ends at 9, 0, starts going vertically upwards, and ends going vertically downwards. So you see how easy it was to control the shape of that curve, the path of that curve, by defining the equation in that way. Yeah. Now let's define another equation, another P equals GMQ. Let's hold that plot. And this P equals GMQ, I'm going to keep my M the same because I'm still working with a Hermite family of curve. I'm going to keep my Q the same. I still want to go from 0 to 1. But I'm going to change my G. Previously, my G was this. I'm going to change my G so that it starts at the end point of the previous curve. So that was 9, 0. It's going to end at 18, 0, further along the x-axis. And this time it's going to start with a vector that is a velocity vector that's pointing downwards, just like the last curve left off, but it's going to end pointing upwards. Yeah? So let's calculate that again. P equals G times M times Q. Here are my P values. Let's plot those. We're going to plot them in red now. And there we have our second piece of the piecewise cubic curve. And can you see how it's joined with C1 continuity? Yeah? It's the end point of the first curve matches the start point of the second curve, and the end velocity of the first curve matches the start velocity of the second curve. So that would have been much harder to achieve had we had to work out somehow the values of the position, the velocity, the acceleration, the rate of change of acceleration for both curves. Right, has anyone got any questions on that? So the Hermite family of curve is a more controllable way of expressing cubic curves and useful for piecewise curve modeling. Okay. Okay, so just as an aside, first of all, I've talked a couple of times about the tangent to a curve now, the velocity of the particle as it moves along this curve. If this is my equation for a curve, P of S is GMQ, I've just written out the Q there, then what would the first derivative of this equation be? The equation, in other words, to get the velocity of that point at any position S along the curve. How would I calculate the first derivative of this equation with respect to S? Would G change? No, because there's no S's in G. Would M change? No, because it's just constant. Would Q change? Yes, so what would Q change to? Oh, I remember differentiation. It's that thing I did at school. It's 3s squared, right? 2s, 1, 0, yeah? Okay, so that's our equation. That's our P dash of S, our first derivative of the equation. It's the same, it's Gm, but then the Q has changed now to this Q dash, this first derivative of Q with respect to S. Okay? So that's how we calculate our velocity at any point on the curve. Okay, so now let's do something a little bit different. Let's think about why we had that matrix M with those 16 values in it. How can we derive those 16 values and explain why they are that way. Well, in order to do that, we're going to use this equation then for a Hermite cubic curve. Remember, the equation for a Hermite cubic curve is just simply P of S is equal to GMQ, where the M is that particular blending matrix, yeah, for the Hermite curve, for the Hermite family of curves. What we're going to do is write out the equation a little bit like I did just in MATLAB there. I'm going to add another column into Q, which will spit out two vectors now. In my example there, I added about 1,000 columns into Q and I got 1,000 points out. This time I'm adding 2 in to get 2 points out. But actually, the first column is going to be my Q, and my second column is going to be my first derivative of Q. So what I'm going to get out on this side, on the left-hand side, is a point at S and a velocity at S, evaluated using this single equation. Does everyone see that? Okay. So what would happen then if I did this? I instead of putting 2 columns in here, I put 4 columns in here, and the first 2 columns are going to be my normal Q, and my second 2 columns are going to be my first derivative of Q. I'm going to get 4 points out the other end, right? Okay, and what I'm going to do is define those 4 points exactly as I would normally. So I'm going to say, okay, I'm going to have the start point of the curve, the end point of the curve, the start tangent of the curve, and the end tangent of the curve. And on this left-hand side, that will then give me, if I populate these values here with the s's from this side, what I'm going to do is compute p of 0. In order to compute p of 0, I have to put s equals 0 here, evaluate this column, so this would be 0, 0, 0, 1. If I want p of 1, then this second column is going to be 1, 1, 1, 1. If I want p dash 0, then this is going to be 0, 0, 1, 0. And if I want p dash of 1, the velocity at the end, this is going to be 3, 2, 1, 0. Yeah? So this equation here is saying, basically, give me the point at the start, the end of the curve, the tangent at the start, the end of the curve. But the curve itself has been defined by a matrix that looks exactly like that. Yeah? So, just substituting in the s's then, we've got this equation here. We've got this quantity here and this quantity here, these two matrices that are the same, times m times this matrix of constants. So, in other words, I can factor out those first two matrices. I get the identity matrix is equal to m times this matrix here. Therefore, m is equal to the inverse of this matrix. What is the inverse of this matrix? This is the matrix we populated with those values for S, remember? The spatial ones, sorry, the positional ones are the first derivative ones. What is the inverse of that? Well, put it in MATLAB. So the matrix is 0, 1, 0, 3, 0, 1, 0, 2, 0, 1, 1, 1, 1, 1, 0, 0. So what is the inverse of that matrix? MATLAB has the handy im function. It tells us that it is exactly that matrix that I told you was the Hermite blending matrix. Yeah? So that's how we derive the Hermite blending matrix. Yeah?
So this is a fixed matrix that is going to change.
Yeah. That's absolutely right, yes. So the question is this a fixed matrix? Yes, that matrix M is the same for any Hermite curve. So it doesn't matter where the curve is in the image or in space, that matrix is always the same matrix for Hermite curves.
What about taking into account the sectional differential?
Well, the Hermite curve is defined as a curve that is controlled by its start and end point and tangents. So we don't need to consider the second differential because that's not the point of the Hermite curve. Okay? All right, so that is the Hermite family of curves. As we can see, it's quite useful family in order to be able to define the curves in piecewise form with C1 continuity. So let's have a look at the Bezier curve family, which is another kind of, another family of curve. And because it's another family of curve, we've got a different blending matrix, a different 4x4 blending matrix that we stick into the equation here. Look it up in the textbook. There it is. That's the equation. That's the matrix. This matrix derives from something called the Bernstein polynomials. We won't have time to cover it on this course. That's for you to look up if you want. You can derive it similarly. If you were to take your P equals GMQ framework then and insert an M that looked like this into it, the Bezier blending matrix, then what we'd get then is, of course, it would change the meaning of our G. Our G no longer means start and end point, start and end tangent. Our G means something else. This M has influenced it. And now the meaning of these four vectors in G are actually, they mean 4 points in space. There's no derivatives in here at all. The first entry in G now means the start point of the curve. Actually, it meant that also for the Hermite curve. The end point, the fourth entry in here, means the end point of the curve. But the two entries here in the middle are also points in space. They're points the curve approximates or moves close to in general. Okay, so this blue curve here is an example of a plot of a Bezier curve. It starts at a start point, it ends at a P of 0, it ends at P of 1, that's the blue curve, but it only gets close to A0 and A1. Yeah, actually that shouldn't be in brackets, that's not a function, that's a constant, so that should be A subscript 0, A subscript 1, apologies for that. Okay, so the curve then, as we iterate, we go from P of 0 to P of 1, it starts off at P of 0, it gets close to A0, gets close to A1, and ends up at P1. And in general, for a Bezier curve, all of the points that we travel through as we iterate along the curve fall within a convex polygon defined by those 4 points, okay? What we call the control polygon of the curve, right? So hopefully you can see that if you wanted to create a Bezier curve that was C0 continuous, that had that basically joined, so it started at the end point of the previous curve, so the second piece started at the end point of the previous curve, then you would just simply have to ensure that the point, the P0, is the P1 of the previous curve. Yeah, does that make sense? Yeah? Okay. It turns out that it's possible to ensure C1 continuity with the Bezier curve as well by ensuring that the join point here is collinear with A1 of the first curve and A0 of the second curve. And moreover, those points, those are 2 approximating points, are equidistant from that join point. If those conditions are true, then the curve will be C1 continuous as well. So it also makes it quite easy to model a C1 continuous curve. If the points are collinear, but they are not equidistant, for example, this point might be much closer to the join point than this point, but they still share a line, then we say the curve is actually G1 continuous, which means basically that the velocities point in the same direction at the join, but they don't necessarily have the same magnitude. Anyway, that's not so important for this course, and neither is the proof of that. We're not going to have time to look at that. But basically, this is how we control Bezier curves. And I guess the takeaway message is that the blending point changes, and it changes the meaning of these points. But what we could ask ourselves is why the curve does behave in that way. So first of all, let's just check, is everyone happy with what I've said? Is there any questions on how the curve's behaving there, the Bezier curve? Okay. All right, so let's look at why then the curve does behave in that way. And this actually starts bringing out the reason why this matrix M is called the blending matrix. Let's look at the effect that this matrix has on these vectors when the multiplication P equals GMQ is calculated. Let's just look at the M times Q part of that equation. When we multiply this matrix with this M, with this matrix Q, then what we're doing is we're, if you remember, taking this first row here of this matrix, multiplying and place for place multiplying that row on top of this column, summing up the results to get a value for the output, which in this the case of this multiplication here will be a vector. Yeah. So the first element of that vector, the first element of the 4 in that vector is going to be minus s cubed plus 3s squared minus 3s plus 1, which I've written out here. And if we do that for all of these rows, then we end up with this multiplied out equation here. So this is a vector containing 4 quantities here, expressed in terms of S, so 4 polynomials in S. Yeah? So what happens then when I complete the multiplication? If I've got this vector here, which is just 4 by 1, and I'm pre-multiplying it by this matrix here, then it's going to basically give me a point that is the result of this, which is just a scalar, just a number when we plugged our s's into it, this times this, plus this times this, plus this times this, plus this, s squared, s cubed, sorry, times this. All added together is our point, the location of our point. Everyone see that? So I've written it out here. So let's look at a plot of these 4 polynomials in S. Let's start with the easiest one, s cubed. What does that look like? Well, I've written in purple here, it just looks like this. We all know what s cubed looks like. Okay. What does minus s cubed plus 3s squared minus 3s plus 1 look like? Well, you're welcome to verify this on your graphical calculator, but it looks like this blue line here. Okay. And the middle two, corresponding to A0 and A1, look like this red and this green curve respectively. So when I'm multiplying these equations together, then what I'm actually doing is I'm saying P of S, my point, is a weighted average of these 4 points in G. And the weight that controls it is these equations here, controlled by S. So when S is 0, this is a plot here of S versus the 4 functions here in the different colours. When S is 0, then the only equation there that's going to come to anything is going to be the first one. It's got this plus 1 on the end. Okay, so blue is at 1 when S is 0. That first term is at 1. Everything else is at 0. So P of S is going to exactly equal P of 0 when S is at 0. Yeah. But then look what happens as S increases. The weight on that first vector, the P of 0, decreases, and eventually it tails off to 0. But in the meantime, the weight, think of these like 4 magnets. This is like the strength of the magnet attracting the point towards it's the weight. It's increasing now, such that the point gets attracted towards A0, but then that starts to wane before the attraction towards A1 increases. That starts to decrease. Indeed, all 3 start to decrease towards 0. And finally, we have the point being attracted solely towards S cubed, so the fourth, so this is, attracted toward P of 1, which is weighted by S cubed. So, can you see how that equation is working now? Any questions on that? Okay, so that's 2 really convenient ways then to model shapes using piecewise cubic curves. An individual cubic curve is easy to control using this mechanism. And it's easy to also to ensure C0 and C1 continuity with both families of curve. Okay, I think we'll finish up today looking at 2 splines, and I might leave the Frenet frame to next time. So the Catmull-Rom spline is another family of curve, but it's a family of curve, actually has a special name. It's called a spline. So the word spline comes from mechanical engineering. And in fact, technically, the Bezier curve is a kind of spline as well. So the idea here is, in fact, Bezier was one of the first to propose this. He was actually a mechanical engineer, and a spline in mechanical engineering, if you're doing metal work, is a very thin strip of metal that is shaped into a particular curve by hanging it between 2 benches, by fixing it between 2 benches and hanging weights on strings along the piece of metal. Okay, so you can sort of see how those would be the approximating points in that equation. In fact, so Bezier came up with that equation to model the shape of metalwork, but it's used extensively now in vision and graphics. The Catmull-Rom spline is a way of modelling cubic curves in piecewise form as well, but it works in a slightly different way because it deals with sequences of control points, of these points. We can go beyond just P1 to 4 of our control points now. We can go to an arbitrary number of control points. And the Catmull-Rom spline enables us to interpolate through all of those points. Okay, so if you think last time, the Hermite curve interpolated 2 points, yeah? Interpolate means pass through, yeah? The Bezier curve interpolates 2 points, but approximates 2 points, yeah? By the way, which condition do you think it would take for a Bezier curve to interpolate all of its points? There's one situation where that would happen. Straight line, brilliant, thank you. Yes, exactly. Yes, because then the control polygon itself becomes a line. Otherwise, in general, it approximates those 2 points. So the Catmull-Rom spline, it will interpolate all its control points with C1 continuity. So this is a super useful thing to be able to do. Define a curve of arbitrary number of control points, arbitrary shape, that can be C1 continuous guaranteed all the way along. This was actually designed by Ed Catmull and Rom, I forget his first name. Ed Catmull, of course, one of the founding partners of Pixar Animation, who went on to found that using these modelling techniques. So, okay, so with the Catmull-Rom spline, because it's a different family of curve, we have another blending matrix. This is the blending matrix right here. In fact, technically, it's half of these values. So I've just, for clarity of notation, I put the 1/2 factor outside this matrix here. Okay, but otherwise, we've got our P equals G MQ. But because the blending matrix has changed, the meaning of these 4 points has changed in the geometry matrix. So what do they mean now? Well, the middle 2 points are points that the curve will approximate. Sorry, that's wrong. The middle 2 points are the points the curve will interpolate, specifically the start and the end point of this piece of the curve. But A and B are the points that the curve will approximate. So, for example, if I were to define this equation here using this G2, okay, so the equation would be P1, P2, P3, P4, okay, then the curve is going to interpolate P2 and P3, and it will get close to A and B, which is P1 and P4 here, but not actually pass through them within that iterating range 0 to 1. Okay, so in order to create a piecewise curve that passes through all of these control points, we have to actually evaluate a sequence of these P equals GMQ equations where we substitute in a different geometry matrix for each bit of the curve, each piece of the curve. So, for example, if I were to put in this G3 into this geometry matrix here, I get a curve that interpolates P3 and P4. So I get this next fragment of the curve here. And so on for as many control points as I want. If I want to get this very first section, I just duplicate the approximating point with the interpolated point. So I go P1, P1, P2, P3. And similarly at the end, I go P4, P5, P6, P6. I don't know why there isn't a P6 on there, but there's meant to be. So in general then, we can interpolate through any number of control points by evaluating a sequence of these P equals GMQ equations. Does that make sense? I've demoed this. So let me check. Okay, so in this code here, I have some code. In this case, it's going to ask for 8 control points, but it can be any number of points. This is in your lab code, by the way, so you can play with this as well. Here I'm defining my Q just as before, to go from 0 to 1 in small increments. I'm going to have my M, which is the blending matrix for Catmull-Rom blending matrix, so it's 1/2 times those numbers I just showed on the previous slide. And then I'm going to have this loop here that goes through a sequence of these P equals GMQ equations, each time evaluating with a different G, which is pulled as a row from this matrix master G, which is a sort of master matrix of G's that different rows correspond to that sequence I showed on the previous slide. So let's run this. I have to click some points. So I'm going to click, let's see, here, 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 here. And there I have a curve which has interpolated all of those points with C1 continuity. That would be really hard to do by guessing a sequences of positions, velocities, accelerations, and rates of change of accelerations. Okay, let's look in briefest detail at the next slide, which is the beta spline. The beta spline is basically the same, except it generates a curve that approximates with C1 continuity all of its control points rather than interpolates them. So this would be a great way of doing like a curve of best fit or smoothing out some data. Because it's a different family of curve, it has a different M. Otherwise, the operation with that sequencing of the G's is the same. So let's do the demo of that. All I'm going to change in this code now is the M. I'm going to swap that blending matrix for the beta spline blending matrix. Let's click. 1, 2, 3, 4, 5, 6, 7, 8. And there we have the approximating curve, which is smoothed out to some degree anyway, those points. Okay. Great. Yeah, there is a final thing I want to say about this, but I don't want to rush it, so I think I'm going to leave it off there. Has anyone got any questions at all on anything on the splines? Yeah. Yeah, that's right, absolutely. Yeah, it's just, we're not going into, for these two splines, we're not going into the detail of why the blending matrices are the way they are, but it is indeed the case that for the beta spline, the values are each of these numbers over 6, which is why I've just written as shorthand here to prevent loads of decimals in the slide. For the Catmull-Born spline, the factor was 1 over 2. That's just the way they've been designed. Yeah. Great. Okay, thanks very much.
呢個遠景一啲都唔會廢嘅，我哋暫時休戰。